The purpose of this video is to introduce you to hyperbolic functions, which I believe many of you have not seen. They are not strictly necessary, but you could use exponentials instead. But the book uses them, and they occur sufficiently often as solutions to integrals and differential equations, and the properties are sufficiently similar to the properties of trigonometric functions that I think they're well worth learning about. So the hyperbolic functions are a natural extension of trigonometric functions. You can obtain them by essentially rotating the complex plane by 90 degrees. To see what I mean by that, I think the easiest way to start is to write down the normal trigonometric functions in terms of exponentials. So we showed in the complex video, the complex numbers video, that you can write that cosine of x equals 1/2 times e to the ix plus e to the minus x, e to the minus ix. And that sine x, similarly, is given by 1/2i times e to the ix minus e to the minus ix. So those are the trigonometric functions. The hyperbolic functions, on the other hand, you can obtain those by simply removing all the i's in here. So we have the hyperbolic cosine. It's written K-O-S-H, pronounced cosh. So the cosh of x, the hyperbolic cosine of x, is 1/2 e to the x plus e to the minus x. And similarly, the hyperbolic sine, or cinch, of x is 1/2 e to the x minus e to the minus x. So they're really just exponential functions, but they're very similar to the cosines. Essentially, you get that cosh of ix equals cosine of x, or that cosh of x equals cosine of minus ix, and same thing for sines. That's what I'm saying, that essentially it involves rotating the complex plane by 90 degrees, so that you're working along the imaginary axis instead of the real axis. So if you plot them, we know, of course, that what the regular trigonometric functions look like. We have these kind of nicely periodic functions that are maximized by the number 1, and they repeat along the x-axis like this. Hyperbolic functions are somewhat different. They look like this. So they are exponentials. If you move away from 0, cosh of x and sinh of x will approach e to the x, or 1/2 e to the x. You can see that because as you move towards large x, these factors here, these terms here, will be negligible compared to these, and essentially it just becomes e to the x over 2 at large x. So, so if x goes to infinity, this becomes essentially goes as 1/2 e to the x. Same thing for sinh. If you go to minus infinity, then cosh becomes e to the minus x, and sinh becomes minus e to the minus x. But other than that, it's the same. We can also see that if we were to take the limit of x goes to 0, then cosh becomes equal to 1, and sinh becomes equal to 0. Just like the cosine and sine functions. In fact, sinh is approximated by a straight line through the origin, just like sinh, and the slope, in fact, is 1 in both cases. In addition to cosh and sinh, you also have the equivalent to the tangent function for the trigonometric function. We have tang, hyperbolic tangent. So tang of x is just sinh of x divided by cosh of x. And if you plot it, it looks like that. Okay. So you have here the slope of 1. And then for large values of x, large positive or negative values of x, tangent of x goes to 1. So you have asymptotic 1 or minus 1. This function approaches as x grows or diminishes. Let me make a table here of the properties of the hyperbolic and the trigonometric functions and how they compare to one another. So first of all, the trigonometric functions, as we know, are periodic. They repeat. Hyperbolic functions are exponential. And in fact, you could calculate only with the exponential functions if you like to. Second, and this is something I didn't point out up here, cosine is an odd even function, and sine is an even function. That doesn't depend on the presence of the i's here. So cosh is even, as you can see, and cinch is also odd, just like sine. So we have that. Like I said before, we also have that just as sine x equals 0 and just as sine 0 equals 0 and cosine 0 equals 1, we have that cinch of 0 equals 0 and cosh of 0 equals 1. If you want to be a little more precise, we can say that we know that when sine of x, when x goes to 0, is approximately equal to x. Cosine x, when x goes to 0, is approximately equal to 1 minus x squared. Similarly for the cinch functions, cinch x when x goes to 0 is approximately equal to x, just like the sine function. But cosh of x equals to 1 plus x squared. And we can see that if we look at these, at the plots again. Cosh is an upwards turn parabola, whereas cosine is a downwards turn parabola. So that's why you have a plus sign in front of the x squared here, minus sign in front of the x squared term in the cosine Taylor series. Next, we can look at the derivatives. So if you look at the derivative of cosine x, we know that that equals minus sine of x. Similarly, the derivative of sine x equals cosine of x. For the hyperbolic functions, it's actually even simpler. There's no minus sign there. So if I take the derivative of cosh x with respect to x, I just get cinch x. Similarly, the derivative of cinch x with respect to x is cosh x. Finally, we have this very important identity for the trigonometric functions. It says that cosine squared of x plus sine squared of x equals 1. For the hyperbolic functions, it's a little bit different, and I'm going to calculate it up here. Let's say that I want to calculate cosh squared of x minus sin squared of x. That's equal to, if we now remember what the functions were for cosine of cosh of x, that's 1/2 e to the x plus e to the minus x. Let me square that. And we do the same thing with the sinh x, except we have a minus sign in front. So that's 1/2 e to the x minus e to the minus x squared. Like that. And this is going to be equal to now 1/4, and then we look at the square of this. Now if I take the square of e to the x plus e to the x squared, that's equal to e to the x times e to the x plus e to the well, actually, e to the x squared plus e to the minus x squared plus 2 e to the x times e to the minus x, but that's just e to the 2x plus e to the 2x plus 2 times e to the x minus x, and that's just equal to 2. So if I plug this result in here, I just get supposed to be a minus sign there. And then similarly for the sinh function, and then we can cancel a few things here. Let's see, that goes away against that, and this against that. And then we are left with 2/4 plus 2/4 equals 1. 1/2 plus 1. 1/2 is 1. So the corresponding formula for hyperbolic function is that cos squared of x minus sin squared of x equals 1. And that's actually the reason why the functions are called hyperbolic. Okay, so let's create some more space here, but let's keep those two things in view here. Now, if we are looking at the cosine squared x plus sine squared x equals 1, let me rewrite it here as cosine squared theta, or phi, if you consider it an angle, plus sine squared of phi equals 1, and then we take x equals cosine phi, we take y equals sine of phi. If you make that identification, then we get that x squared plus y squared equals 1. Well, that's the equation for a circle, right? It looks something like this. And if you pick a point here on this circle, like there, then this angle here is phi, or over here we have sine of phi, and down here we have cosine of phi. The length of this line is 1 because it's the unity circle. Now let's look at the hyperbolic functions for a second. We have cos squared of alpha minus sin squared of alpha equals 1. If we make then the substitution that x equals cos of alpha and y equals sinh of alpha, then we get x squared minus y squared equals 1. Just as the x squared plus y squared equals 1 is the formula for a circle, x squared minus y squared equals 1. A little hard to see there. Is the formula for a hyperbola. So if you plot it, it looks like this. And we can do the same thing as we did here. We can just draw a line from the origin to some point on the hyperbola. That's that point there. Then this is now equal to cos of x. And over here we have sinh, not of alpha. It's not cos of x here, it's cos of alpha. So alpha is the parameter that we use to describe this curve. So here the parameter was the angle phi. Here it's alpha. It's not so clear, though, just looking at this, what is the meaning of alpha. Phi here clearly is the angle from the x-axis to this line here. Position vector if we're working in polar coordinates, and then this is the position. It turns out, and you can show this for yourself if you're interested by taking the integral, that this area here between this hyperbola, this line, and the x-axis, that area is alpha over 2. So that's the parameter. And that actually underlies the names for the inverse of the hyperbolic functions. We know that if, let's say, x equals sine of phi, then we also can write that phi equals arc sine of x. Now sometimes people write sine to the minus 1 of x. I don't like that notation because when you write sine squared of x, that means the squared of sine x, but this now should mean the inverse function, but it might also mean 1 over sine of x, so it's a little bit ambiguous. So I prefer this notation. Arc here, this arc here refers to arc length. It's the arc length corresponding to this angle phi here. Since we are working on a unit circle, and if we're working in radians, as you should, then the length of this arc here is phi. And that's the phi you get when you take the arc sine of x. For hyperbolic functions, if we have that x equals cinch of phi, if we invert this, then we get that alpha equals r cinch of x. So note now that there's no c here. The r here actually stands for area, this area here. So the book actually uses the wrong nomenclature. There's no c in r sine. It's just a-r-s-i-n-h and r cinch. Okay, so that's a little bit about the hyperbolic functions. They will mostly occur in what we do as solutions to differential equations and integrals. And like I said, you can eschew them and only work with exponentials, but it is quite convenient to use them in many cases because they have properties that are very similar to those of the trigonometric functions.